Welcome back to Things I Know Nothing About. I'm Maya, and joining me as always is Alex. How are you doing today?
Doing great, Maya, and honestly, today's topic has me unreasonably excited.
Okay, so I saw the headline and I thought someone was joking. We're talking about putting data centers in space.
Not joking at all. In fact, this is one of those rare stories where the US and China made almost identical announcements within days of each other. Both countries are now racing to build AI computing infrastructure in orbit, solar powered server farms circling the Earth.
When people said their files were in the cloud, I didn't think they meant literally above the clouds.
Right? The metaphor is becoming physical reality, and the stakes are enormous. We're talking about the future of AI, energy policy, and great power competition, all colliding about 500 kilometers above our heads.
Let's start with the obvious question. Why would anyone want to launch a data center into orbit when you could just build one on the ground?
Fair question. The short answer is power and cooling, the two biggest headaches for AI infrastructure on Earth right now. Training large AI models requires staggering amounts of electricity. A single large data center campus can consume as much power as a small city.
And we're running out of places to plug them in?
Essentially, yes, there's a global scramble for grid capacity. New data centers are being delayed because the electrical grid literally can't supply enough power. Some regions have moratoriums on new construction. Meanwhile, cooling is the other nightmare. Many facilities use millions of gallons of fresh water for evaporative cooling towers.
So space solves both of those problems.
In theory, beautifully, in orbit, you get near continuous sunlight, no clouds, no nighttime if you choose the right orbit. Solar panels in space generate roughly 5 times more energy per panel than ground installations because there's no atmosphere filtering the light. And for cooling, the vacuum of space is essentially an infinite heat sink. You radiate waste heat as infrared energy directly into the void.
That's kind of poetic, actually. The void of space keeps your servers cool.
It is no water needed, no evaporation towers, no fights with local communities over water rights. Elon Musk summed it up at Davos in January. He said, quote, "It's a no-brainer building solar-powered data centers in space. The lowest cost place to put AI will be space, and that will be true within 2 years, three at the latest."
2 to 3 years. That feels wildly ambitious.
Musk timelines are famously aspirational, but the underlying physics actually checks out. The question isn't whether space-based compute makes theoretical sense, it's whether we can engineer it affordably and reliably.
So who's actually building this stuff? Is it just SpaceX?
Not even close. There's a whole ecosystem forming. Let me walk through the major players. First, there's Google with Project Suncatcher announced in late 2025. They're partnering with Planet Labs to launch two prototype satellites by early 2027, each carrying Google's own TPU chips, their custom AI processors.
Google is sending their TPUs to space, the same chips they use on the ground.
Exactly the same hardware. They tested the chips by blasting them with a proton beam in a lab to simulate space radiation, and the TPUs survived nearly 3 times the dose they'd encounter in orbit. The long term vision is constellations of 81 satellites arranged in kilometer wide arrays connected to each other by laser links.
81 satellites talking to each other with lasers. That sounds like science fiction.
Then there's Starcloud, formerly called Lumen Orbit, a Y Combinator startup out of Redmond, Washington. They actually made history in December 2025 by training the first AI model ever in orbit. They sent up a 60-kilogram satellite, about the size of a small fridge, with an NVIDIA H100 GPU on board.
Wait, they already did it? An AI model running in space?
Running and responding, they loaded Google's Gemma language model onto the satellite and were querying it from Earth. The CEO, Philip Johnston, said it was 100 times more powerful GPU compute than anything previously operated in space. Their ultimate goal, a 5 gigawatt orbital data center with solar and cooling panels roughly 4 kilometers across.
4 kilometers. That's larger than most neighborhoods.
And then, of course, there's SpaceX itself. Musk confirmed in October 2025 that SpaceX will be doing data centers in space, suggesting that next generation Starlink satellites could be scaled up for compute workloads. The proposed SpaceX XAI merger, reported just this week, would combine Rocket's Starlink's satellite network and XAI's Grok chatbot under one roof.
Which gives them the full stack, the rockets to launch it, the satellite network to connect it, and the AI to run on it.
Precisely. SpaceX is targeting a massive IPO this year, potentially valued above $1 trillion, and orbital AI infrastructure is reportedly a key part of the pitch to investors. Bezos and Blue Origin are exploring it too. He's predicted that space facilities will outperform Earth-based servers within decades.
Okay, so that's the American side. What about China?
On January 29th, literally yesterday, as we're recording, Reuters reported that China's main space contractor, CASC, the China Aerospace Science and Technology Corporation, released a 5-year development plan with some jaw-dropping ambitions.
Such as,
They pledged to, quote, construct gigawatt-class space digital intelligence infrastructure. The plan calls for a full space cloud by 2030 that integrates cloud, edge, and terminal computing capabilities, processing Earth's data directly from orbit.
gigawatt class. For context, how much power is that?
A gigawatt is roughly the output of a large nuclear power plant, so they're talking about nuclear plant levels of solar power generation in orbit dedicated to AI compute. The CASC policy document from December identifies this as a core pillar of China's upcoming 15th five-year plan, their national economic roadmap.
That tells you they're dead serious. 5-year plans aren't aspirational blog posts.
No, they're binding government strategy, and the plan goes further. CASC also announced they'll achieve operational suborbital space tourism within 5 years, then gradually develop orbital tourism. Plus, China just inaugurated its first school of interstellar navigation at the Chinese Academy of Sciences.
Interstellar navigation, as in between stars?
They're thinking very long term. The school covers interstellar propulsion and deep space navigation. Xinhua, the state news agency, wrote that the next 10 to 20 years will be a window for leapfrog development in China's interstellar navigation field.
So they're simultaneously building space data centers, launching space tourism, and training people for interstellar travel. Ambitious doesn't begin to cover it.
Here's the geopolitical context, though. China's key bottleneck right now is reusable rockets. SpaceX's Falcon 9 is already reusable. That's how Starlink achieved near monopoly status in low Earth orbit satellites. China hasn't completed a reusable rocket test yet. Their Long March 12A recovery attempt failed in December 2025.
Which matters because
Because reusability is everything for cost. If you can't reuse your rockets, every satellite launch is dramatically more expensive. China achieved 93 space launches in 2025, a national record, but none with recovered first stages. SpaceX routinely lands and relaunches boosters, sometimes within days.
So China has the ambition and the government backing, but the US has the engineering lead on the delivery mechanism.
That's a fair summary for now, though China's commercial space startups like Landspace are maturing rapidly and hoping to complete rocket recovery by mid-2026. This could change faster than people expect.
Let me play devil's advocate for a minute. This all sounds incredible, but what are the catches?
Oh, there are plenty. Let's start with thermal management. Yes, space is cold, but there's no air to carry heat away through convection. All cooling has to happen through radiative panels that emit infrared energy. NASA studies show these radiators can account for over 40% of a spacecraft's total power system mass at high power levels.
So your cooling system might weigh more than your actual computers?
Potentially, yes. Designing compact systems that keep dense AI chips within safe temperatures is one of the hardest unsolved problems. Then there's maintenance on Earth. Data center technicians swap out failed drives, upgrade components, and patch hardware constantly. In orbit, you'd need robotic servicing missions or entirely new satellite launches to fix anything.
Every hardware failure is basically a write-off.
Unless you have autonomous repair capabilities, which don't really exist yet at scale. Networking is another massive challenge to replicate the kind of high bandwidth, low latency interconnects that modern AI training requires. You need laser communication links operating at multi-terabit capacity between satellites that are zooming past each other at thousands of kilometers per hour.
Maintaining a laser link between two objects, both moving at orbital velocity, sounds nightmarish.
It requires extraordinary precision, orbital drift, alignment maintenance, weather disruptions for the ground links. All of these degrade performance. And then there's economics. Google's own Project Suncatcher paper estimates that launch costs need to drop below $200 per kilogram by the mid-2030s to make space data centers cost competitive. Right now, we're at roughly 7 to 8 times that.
So the business case depends on Starship or something similar, absolutely crushing launch costs.
Exactly.
SpaceX's Starship is the linchpin. If Starship achieves its promised cost per kilogram, the economics flip. If it doesn't, or if there are significant delays, orbital data centers remain a science experiment rather than a business.
And radiation. These are sensitive electronics, right?
Google's proton beam tests are encouraging. Their TPUs survive 3 times the expected orbital dose. But that's a lab test. Maintaining reliable performance for years through solar storms, cosmic ray events, and cumulative radiation damage is a completely different challenge. A space-based data center can't afford the kind of random bit flip errors that radiation causes in sensitive AI computations.
This is the thing I love about these stories. The physics says yes, the engineering says maybe, ask me later.
Here's what I think is the really profound takeaway. For decades, the cloud has been a clever marketing term. Your data isn't floating anywhere. It's sitting in a concrete building in Virginia or Oregon, consuming megawatts and millions of gallons of water. Now, for the first time, the cloud might actually become orbital,
Literal cloud computing above the actual clouds.
and the geopolitical dimension is fascinating. Whoever controls orbital compute infrastructure could have enormous advantages, not just in AI development, but in Earth observation, communications, and even military intelligence. The US-China space race used to be about prestige and moon landings. Now it's about server racks and solar panels.
Do you think this actually happens on the timescale people are talking about?
Prototype missions, absolutely.
Google's Suncatcher satellites in 2027, Starcloud already flying, industrial-scale orbital data centers replacing terrestrial ones. That's probably a decade-plus timeline, and it depends on launch costs falling dramatically. But the trajectory is clear, and both superpowers are committing serious resources.
Well, the next time someone tells me their data is in the cloud, I'm going to ask which orbit.
Low Earth, most likely, about 550 kilometers up, completing one lap every 90 minutes.
Of course, you'd know the exact altitude. That's our show for today, folks. If you enjoyed this episode, subscribe wherever you get your podcasts and leave us a review. We'll see you next week on Things I Know Nothing About.
Clear skies and clear server logs.